Hello everyone and welcome to another episode of Rob's video blog. Thanks for taking the time and watching the video. Today I would like to talk about problem solving and truth seeking. And when I talk about problem solving and truth seeking, I mean problem solving and truth seeking in any aspect, mathematical problem, historical inconsistencies, interpersonal problems, language problems, trying to just explore and discover the truth about something that you didn't know about or something you're interested in, anything. But one of the most important things when trying to find the truth or solve a problem is to have a methodology. If you don't have a basic framework of methodology, you're just kind of, spitting or pissing into the wind and hoping that what you end up with is correct. One of the most important advancements man has ever made is the discovery and the implementation of the scientific method. It's, you have a question about something, about how something functions, you propose a hypothesis, you test it, you check the results, and if the results corroborate your hypothesis, you explore it further. If the results do not corroborate your hypothesis, then you have to adjust your hypothesis and continue to test. And this is how the implementation of the scientific method has literally launched our species on a meteoric rise to dominating the planet and developing civilization and the technology and all the niceties that we take for granted today. If it wasn't for the scientific method and the implementation of it, it's very possible we would still be living with a Ptolemaic system in which we think, the Earth is the center of the universe and so on and so forth, and we may still be scribbling on tablets rather than playing Angry Birds on them. Why do I think that this is an important thing to be talking about right now? I think it's really important because unfortunately the use of the scientific method and a consistent methodology for seeking truth and solving problems has given us a lot of solutions to a lot of problems that previously were not off-the-shelf answers. In other words, I'm an engineer. When we design things and we build things, there are very few scenarios where we actually have to solve the problem or do a calculation or solve an equation by hand from scratch, because if you need to build a building this big and it weighs this much, or you got to build a bridge and you're gonna have cars on it, you have member sizes, there's all tables. People have already calculated most of this stuff, and you just kind of pull the appropriate information off of tables and you just kind of plug them in where you need them to. Lots of problems have already been solved. So it's very convenient because then we don't have to sit here and think about everything. There's already solutions been done for us, and we just pull them as we need them and we use them in our everyday life. The only problem with that is that when we do get confronted with a problem that there is not a already provided correct solution, we are kind of crappy at coming up with a solution because we don't use it on a regular basis. It's like reading and writing anything else, riding a bike. The more you do it, the better you become at it. And if you don't use it, you fatigue and you atrophy and you lose the ability to do it. You lose your sharpness. So I think that's a lot of what has happened nowadays is we have so many solutions to so many problems. This doesn't work, that doesn't work. Oh, here's the answer, here's the answer. You can buy this, you can find it here, and that's, and like I said, it's really good because there's tons of information out there. But if we don't stop and take the time to occasionally solve a problem on our own, or even take a problem that we have a solution for and explore, well, how did we get to that solution? What is the theory behind it? What are the steps that it took for someone to figure this out? We lose the ability to critically think and solve really complicated, complex problems, and that's a major problem. So one of the easiest ways to solve really complicated problems, and they teach you this, in basic math classes, is you break the problem down into smaller, simpler, easier problems that you know how to solve. Okay, so if you had a really, really long, complicated algebraic equation, you break it down into the small components that you know how to solve. Well, in order to do that, you need to first have the mastery of the basic skills. If I gave you a complicated algebraic equation and said, okay, calculate this or find the solution, find what x is, you'd have to first know how to properly add, subtract, properly multiply and divide, how to use order of operations, fractions, all this kind of stuff, and you'd have to have it mastered and have a really, really good understanding. Otherwise, if I asked you how to solve that, you would have absolutely no shot at doing that. And in fact, if I gave you a really complicated algebraic equation and you said to me, I don't know how to add, subtract, multiply, or divide, but I have the solution to this algebraic equation, I would obviously just dismiss your solution out of hand as being totally and completely ridiculous. Because if you can't solve the basics and don't have a mastery of the basics, there's no way you can solve a complicated problem. So that's probably one of the most important aspects of problem solving that we lose sight of, is we get confronted with a complicated problem, and instead of breaking it down and making sure that we first understand the fundamental components of that problem and have sound solutions to those, we go ahead and try and solve the problem outright, and you're inevitably going to end up with the incorrect solution or the incorrect answer. Aside from being able to better solve complicated problems by having a mastery of the basic principles, more important than that is having a mastery of the basic principles doesn't necessarily guarantee that we can come up with the solution to a really complicated problem, but it allows us to check proposed solutions pretty easily for at the very least, logical consistency. So what I mean is, if I was teaching you math and you didn't know how to add really big numbers, right? You teach little kids, okay, add 2 and 2 and 4, and 4 and 4 is 8, and 2 and 6 is 8, and so on and so forth. And you taught someone, okay, well, here's an odd number, here's an even number, and when you add all even numbers, the answer is an even number. And then I gave you this really, really long problem. It's 480,322,008 plus 46 plus 422 plus 6. And I said, what's the solution? And you would say, well, I haven't learned yet how to add really, really large numbers, so I don't know. But if I told you, well, I'm going to tell you right now, the solution is 9. You would say to me, no, it's not. And I would say, well, you don't know. You just got done telling me you don't know what the solution is and you can't calculate it. How can you now come back and tell me that my solution is wrong? And I would say, well, I don't know how to add really big numbers, but I can tell you that all these big numbers and all these numbers are even, and I know that adding even numbers yields an even number. Your solution is an odd number. Therefore, I know that your solution is incorrect. So this is a very basic example of how having a good understanding of the basic principles can allow us to, at the very least, do a cursory check of proposed solutions. And this is really, 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 really important, because I think a lot of the times it's not so much that we need to come up with an answer, but it's that when other people propose solutions, we have to have a way to at least do a cursory check of whether or not that solution is a valid and true solution. So take some time, think about things and solutions and truths that you take for granted every single day. Spend some time and say, hey, how do I know that this is true? Go through the steps, start from first principles, build it back up to the final solution, and verify and say, yes, I can say with confidence this is correct because I know XYZ and XYZ and XYZ, and I have a mastery of those basic principles. One last thing, or two last things that I want to say about problem solving is, and I find myself falling into this trap all the time. A lot of times there's a proposed question or there's a proposed problem, and we know what we want the solution to be, or we've heard of proposed solutions. So we say, well, here's a problem, boom, and here's the answer. And then we go back and try to prove the answer. That's really not a very good way to solve a problem. If I gave you a mathematical problem, you wouldn't go, the answer is 4,827, and go back and try and justify that. You would take the problem and you would work through it and try and come up with an answer. Very often we don't do that. Very often there's a problem or there's some truth that we're looking for, and somebody somewhere or even ourselves have proposed the truth, and we go and try and back check it. We shouldn't do that. That's not the way that you solve problems. The way you solve problems is you look at the problem, you look at the question, you break it down into its smaller components, you rely on the mastery of your basics, you solve the individual, less complex components, and then you can put them together and develop the more complicated relationships, and then and only then will you have a shot at actually coming up with truth or the proper solution. Do not take an answer and try and back prove it to a question, because I mean, literally, I mean, just think about it. If I gave you a really, really long algebraic equation and you were literally just picking numbers and going back and checking them, it would take you your entire life until you actually found the correct number and back checked and said, aha, there it is. So not only is it inefficient, but it's not the right methodology for solving problems. One other thing that I'll say, the last thing before we go, is that in kind of going through these sorts of things and thinking through solutions or truths that we have, and trying to go back to first principles and say, okay, well, here's supposedly the solution that I've taken for granted. How do I arrive at that? How did I arrive at that answer? Or how did somebody who calculated this previously come up with this? You go back to the beginning and you build it up to verify that. Well, in doing that, you're always asking yourself, well, why or how, or why or how? So I have developed a very good appreciation for children, because children are the ultimate skeptics. Children are always going around asking you why, and you always have to prove things to kids. And people get frustrated by it, well, mostly probably because you're really busy trying to get stuff done, and the kid goes, why? But a lot of times, a kid will ask a mother, well, why? And the parent doesn't have a good answer for them, and they just get frustrated and say, well, because I said so, or if you're proposing something to a child, you're proposing something to anyone, and they ask you a very basic question, well, why? And you can't give them a good answer, you really need to examine what you were telling that person. Because if you can't answer a 5-year-old adequately, how, then whatever you're saying or whatever you're proposing probably did not go through a whole heck of a lot of mental and logical rigor. So that's why I do actually like kids. They're the ultimate skeptics. They're always asking why, and they keep us honest. We can, as adults, I feel like we have a tendency to pull the wool over our eyes, and we think that we know a lot more than we do. And kids really kind of bring us down to earth by asking us why and making us prove things to them and being the ultimate skeptics. Because I think at the end of the day, a lot of the things that we think we know, we think we have the answers for, we haven't really gone through the steps to really be 100% certain, and we don't really fully understand it. So yeah, just go back, think about some things, work on your critical thinking skills, master the basics first, and then we can tackle the complex problems. So thanks for watching, and I hope you enjoyed it as much as I did.